So let's start with a simple scenario. It is 2 a.m. Your primary database crashes, completely offline. Now I want you to pause for a minute and think, what happens next? Do your users still see their data? Can they still make payments? Or does your entire system go down? In distributed systems, failure is not an exception. It is a guarantee. Machines crash, networks partition, power fails. The real question is not whether failure will happen. The real question is whether your system is designed to solve it. And that is where replication comes in. Today, we're going to understand replication properly. We'll look at synchronous and asynchronous replication, leader election, and failover. And by the end of this video, you should clearly understand how large-scale systems remain available even when machines fail. Let's get started. So, what does replication actually mean? When people first hear the word replication, they usually think it simply means copying the database to another machine. But in distributed systems, replication is more structured than that. We do not replicate raw database files randomly. Instead, we replicate operations. Every write request, whether it is an insert, update, or delete, is recorded in an ordered log. Each replica then applies those operations in exactly the same order. Now let me ask you something. Why do you think order matters so much? If two replicas apply the same operations but in different sequences, will they end up in the same state? The answer is no. Order determines the final state of the system. That is why replication is really about keeping a consistent order logged across machines. This concept is known as state machine replication. If the order is preserved, consistency is preserved. Most distributed databases implement replication using a leader-follower model. In this architecture, one node is designated as the leader. All write requests are sent to that leader. The leader appeals the write request to its logs, then sends that log entry to the follower replicas. The followers append the same entry to their logs. Now, here is an important question. When should the client be told that their write has been successful? Should the leader respond immediately after writing locally, or should it wait until the replicas confirm the write? That decision leads us to two major replication approaches. First is synchronous replication. In synchronous replication, the leader waits for acknowledgments from replicas before responding to the client. Typically, it waits for a majority of replicas, not necessarily all of them. Let us imagine there are 5 replicas in total. The leader may wait for confirmations from 3 of them. That is called a quorum. The reason for waiting for a majority is safety. If the leader crashes, at least one replica in that majority will still have the most recent committed data. This prevents data loss. Now, think about the trade-off here. Every write must wait for network connection. If one replica is slow or temporarily unreachable, write latency increases. So synchronous replication gives you strong durability and consistency, but at the cost of higher latency. If you're designing a banking system, would you choose synchronous replication? Most likely yes. Now let us consider asynchronous replication. In this model, the leader writes the data locally and immediately responds to the client confirming success. Replication to followers happens in the background. This improves performance significantly because the client does not wait for other machines. However, there's a risk. Imagine the leader crashes right after responding to the client but before the followers receive the update. That most recent write may be lost. Now I want you to think carefully. Would you accept that risk for financial transactions? Probably not. But would it be acceptable for a social media like Counter or analytic metrics? Possibly yes. This is the foundational trade-off in distributed systems: performance versus durability, and speed versus safety. There is no universal correct answer. It depends entirely on system requirements. Now let us move on to failure handling. Suppose the leader crashes. The system cannot just stop accepting writes, but at the same time, we cannot allow multiple nodes to accept writes independently. That would cause conflicting data. There must be exactly one leader at any given time. So, How do replicas decide who becomes the new leader? They use leader election. When followers stop receiving heartbeat messages from the user, they assume it has failed. After a timeout, one of the nodes starts an election and requests votes from other replicas. Each node can vote exactly once in a given election term. If a candidate receives vote from a majority, it becomes the new leader. Now, here's something critical. Not every node should be allowed to become the leader. The node must have up-to-date log, otherwise previously committed data could be lost. Now, let me ask you this. What would happen if two nodes both believed that they were the leader? That situation is called split brain, and it leads to inconsistency. Majority-based elections prevent this by ensuring that only one leader can gain enough votes. Once a new leader is elected, the system transitions to it. This process is called failover. Failover can be manual, where an operator promotes a replica, or automatic, where the system handles leader election without human intervention. In modern high-availability systems, automatic failover is essential. Downtime must be measured in seconds, not minutes. Now let us summarize what we have learned. Replication provides redundancy so that the data is not stored on a single machine. Synchronous replication prioritizes safety and durability. Asynchronous replication prioritizes performance. Leader election ensures that there is only one authoritative node coordinating writes. Failover restores system availability when the leader crashes. Together, these mechanisms form the foundation of fault tolerant storage in distributed systems. But replication alone isn't enough to guarantee agreement across machines. How do systems formally agree on log order? How do they mathematically ensure that only one leader exists? How do they balance strong consistency with availability? In the next video, we'll explore consistency and consensus in distributed systems. We will discuss quorum systems and algorithms like Paxos and Draft. That is where distributed systems move from engineering patterns to rigorous distributed coordination theory. I'll see you in the next video.